Good day to all. We are Lorenzo, Arion, Sage Capistrano, Adrian Perez, and Zachary Ongpeng, BSc students of DLSU, who are guided by our advisor and co-advisor, DLSU CE Department faculty members, Dr. Bernardo Lejano, and Engineer Kenneth Elevado. We would like to present our research to you on increasing concrete compressive strength with the application of aggregate modification treatment methods on coarse ceramic waste aggregates. Next slide, please. Based from their local news media article, ABS-CBN reported last 2018 that 30% of the country's waste comes from the construction industry. With regards to waste generated worldwide, it was stated in a study by Jacob, Agarwal, and Kushwaha last 2017 that around 75% are construction and demolition wastes, from which 54% are ceramic wastes. With this, past researchers have involved the use and shown the potential of ceramic waste in concrete production. The results of one study have shown that 100% replacement of coarse aggregates yielded a 36.1 increase in concrete compressive strength. Despite this, the viability of ceramic wastes is affected by its high absorption capacity. With this study aims to apply aggregate modification treatment methods to investigate if the absorption of ceramic tiles can be reduced and to determine its effect on concrete workability and strength. Next, please. So here we have the three main methods that we use for this study as aggregate modification treatment methods. First, we have cement impregnation. Next, we have slurry wrapping. And lastly, sodium silicate soaking.
So as for our research method and experimental setup, the following batches were prepared. Regular control concrete batches of WC ratios of 0.5 and 0.6, untreated CTW concrete with 25% and 50% replacement values, and WC ratios of 0.5 and 0.6. The treatment methods each had their own batch which followed the parameters of the untreated samples as shown here in this table. The untreated CTW was formed by crushing waste ceramic tiles to match the nominal size of gravel. A portion of the CTW was set aside to apply the treatment methods. So the first treatment method was cement impregnation, and it involves the cement impregnated tiles being produced by soaking the CTW tiles in a mixture of water and cement with the ratio of 1 kilogram cement to 10 liters of water for 24 hours. Moving on, as for the next treatment method, the slurry wrapping, the slurry produced by the next treatment method was made by formulating a mixture that contained the ratio of 10 kilograms cement to 1.5 kilograms fly ash to 10 liters of water. The CTW was then poured into the slurry and was left for 1 hour before drying. As for the last treatment, sodium silicate soaking, it involves soaking the CTW into a mixture that had a ratio of 800 ml sodium silicate to 10 liters of water. And this was soaked in this mixture for 1 hour. So the absolute volume method was used to proportion the components of each CTW concrete batch, and the slump test based on ASTM SEE-01 was used to verify if the workability of each concrete mixture was able to achieve the target 80 mm slump. The samples were then molded into cylinders for periods of both 7 and 28 days before subjected to the compressive strength test as per ASTM SEE-39.
Moving on to our results. First, we have our absorption values where, as you can see, all three treatment methods were able to effectively reduce the absorption of untreated ceramic tiles. On the right, we have a graph of slump versus CTW absorption. And from this, we can see that our initial assumption of low absorption equaling higher slump is actually invalidated, where the treatment with the best slump is actually that of SS, or sodium silicate soaking, with the middle ground absorption of around 11%. This may imply that CTW absorption does not affect workability in a predictable manner. Now, this may also be attributed to other factors such as aggregate shape and texture, which actually vary between the treated CTW. SS may have been the most workable due to it being the smoothest of the treated aggregate, where there is less internal friction among components. Next, please. Moving on to slump versus percent aggregate replacement, as seen in the graph, from 0 to 25% replacement, there is a decrease in slump for 0.6 water cement ratio mixtures, and there is a slight increase in slump for 0.5 water cement ratio mixtures. whereas from 25 to 50% replacement, most of the mixes decrease in slump, whereas 3 of the 0.6 water cement mixtures increase in slump. Now, these results are mostly in line with our predictions, although ultimately the percent replacement did not greatly affect the workability, although slump values at 25% are much closer together as compared to those at 50%, with the exception of SS.
Moving on to compressive strength, here shown is the strength development of all batches. With this, CI batches had the greatest compressive strength increase of 17 MPa from 7-day to 28-day curing. Next slide, please. Next, this figure shows the compressive strength of all samples, considering all independent variables, and was used to show trends between water cement ratio and compressive strength. It was generally observed that for both 7 and 28 days of curing, 0.5 and 0.6 water cement ratio batches yielded lesser and greater compressive strengths compared to the control batches respectively. An exception to the 28-day cured batches would be those treated with CI, which exceeded the compressive strength of the control setup by 6.67 MPa. Next slide, please. Next, this figure only focuses on the comparison between the 28-day compressive strengths of all batches with the control setup. It was observed that strengths from the SS and CA batches were similar and exceeded those reduced by the control setup respectively. Partnered with an acceptable slump, CI-treated CTW concrete may make it more viable for CTW to be incorporated in concrete production. Next slide, please.
So next, here the graph is showing the comparison between the compressive strength and ceramic tile waste replacement with a constant of 0.5 water cement ratio. In the figure, it shows that compared to the control sample, the slurry wrapping method has the worst performance in the 25% replacement category, followed by the untreated and sodium silicate samples, which are more or less on the same level, with cement impregnation sample being the best sample for the 25% replacement category. In the first 50%, however, the cement impregnation is still by far the best with a huge margin, with the other 3 methods having more or less the same results with one another. Next slide, please. On the other hand, in the figure pertaining to the 0.6 water cement ratio of all the samples, the cement impregnation is also still the best, but it is important to note that the 50% replacement category, it is much closer to the other samples' compressive strength. It also has similar patterns to the 0.5 water cement ratio graph, with the exception that the sodium silicate method is noticeably higher in the previous graph. Next slide, please. So overall, the best AMT method is cement impregnation, specifically the CI-C25W 0.5 sample. It also has the CDW absorption of 12.963% with a 11.322% decrease from the control. It also has a slump of 83 millimeters, which is deemed to be workable, and it is within a range of 80 to 100 millimeters. So its compressive strength is 46.68 MPa, and it has a 16.67 increase from the respective control and a 26.72% increase from the untreated setup. It is also important to note that the compressive strength value increased by 4.95% from the 7-day sample. Next slide, please.
So moving on, as for the cost analysis, when considering the costs of all components of the concrete batches produced, it was found that cement impregnation was the most cost-effective treatment since the average price of each CI batch is closest to that of the control batches. Not only that, CI also exhibited the greatest increase in strength relative to the control samples out of all the treatment methods.
So overall, the study arrived at the following conclusions. First, all the tested treatment methods were able to reduce the absorption of the CTW aggregate. And as for the specific treatment methods, the sodium silicate treatment produced mixes with the best workability, although there was no improvement to the compressive strength. The cement impregnated samples exhibited the greatest 28-day compressive strength, in addition to its treatment being the most cost-effective. And the slurry wrapping treatment, on the other hand, was the least effective in improving compressive strength. And as for aggregate replacement, moving from a 25 to 50% replacement showed better results for mixes with a 0.5 water cement ratio over that of the 0.6 mixes. The experimental results have shown that using a 0.6 water-cement ratio would likely yield a decrease in compressive strength. And lastly, the optimum mixture in this study was found to be the cement impregnated mixture with 25% CTW aggregate replacement and 0.5 water-cement ratio. And this is mostly due to the high 28-day compressive strength and little compromise to workability. Now that ends our presentation. Thank you for listening.